So I have this web application that we are working on. It's displaying ECG data. There's a few issues that we're trying to solve. So I have this problem with the window size. The window size is actually changing, so the x-axis is changing. So 10, 8, 6, whatever. But obviously, we're actually logging it. It's always generating the same number of data points. So that's unusual. Right, okay, that was a quick solution that had to remain duration. So now it's changing. Okay, just 1 second. What's default? 5. And let's change the defaults. I'll keep it 90. It's value 3. Right. Okay, this is better. So we can keep generating. It will regenerate when values are changed. I think this isoelectric voltage is not, it's actually doing something.
Neurokit2 is the most welcoming project with a large community of contributors with all levels of programming expertise. But the package is still far from being perfect. Thus, if you have some ideas for improvement, new features, or just want to learn Python and do something useful at the same time, do not hesitate and check out the following guide.
Particularly this function.
Hash generate 15 seconds of ECG signal, recorded at 250 samples per second. ECG equals nk.ac_simulate, duration equals 15, sampling_rate equals 250, heart_rate equals 70. Signals, info equals nk.ac_process, ECG, sampling_rate equals 250.
This is nice. Wait, where is the first plot? ECG simulate as the one we're using. That's a really nice plot. The isoelectric line. It's essentially the baseline. Yeah, there should be a better version of this.
It appears that you're adding the isoelectric voltage directly to the ECG signal. This will shift the entire ECG signal up or down along the y-axis by the amount of the isoelectric voltage. This can simulate a baseline wander or a shift in the baseline ECG signal, which is common in real-world ECG signals due to various factors like breathing, electrode placement, etc. However, if you intend to have a more complex interaction of the isoelectric voltage with the ECG signal, you should specify it. But in real-world scenarios, the isoelectric line can also be affected by noise and other factors, leading to a non-uniform baseline shift known as baseline wander. If you want to simulate that effect, you would need to add a more complex noise or drift model to the isoelectric line adjustment. For instance, to add a more complex baseline wander effect, you might consider adding a low-frequency noise to the ECG signal. In this example, the low_frequency_noise is generated using a sine wave across the duration of the ECG signal. This will simulate a baseline wander that changes over time, instead of a uniform shift.
Yeah, this is not millivolts, is it? It's working better. Should make it from isoelectric voltage from 0 to 1 should suffice. Let's say of 5. It's electric voltage. Yes, that will be default. Well, that looks more like it. Okay, now these things are not being taken account. All 4 variables are not being accessed in the Python script.
It looks like you've extracted these variables from the incoming JSON data, but haven't used them yet. Here's how you can incorporate these variables into your ECG generation and modification process. You can add 50 Hz noise to the ECG signal to simulate the effect of power line interference.
It's adding a 50 Hz sinusoid to the ECG. That's what it looks like so far. We have some of them are not actually, yeah, those delays. Now we're looking at white noise works, even though there's obviously too much of it. Yeah, 0.5 should probably be enough. Can change it straight away. White noise, let's say 0.5, max 0.5. That will be the maximum. The default looking okay. Isoelectric voltage looks okay. Okay, what else? We have this goes into Python code. Can go after the white noise. Right. No, wait. Oh, yep. Okay, default. This is a 50 Hertz noise. There's probably too much of it, but that's okay. Default is bugger all. Yeah, that's okay. PQRS delay.
Snippet creates a sine wave at 50 Hz and then multiplies it by the specified amplitude of the noise and adds it to the ECG signal. For the PQRS and QRST delays in different ECG signal types, you might need to look for a more advanced ECG signal generation library or model, or adjust the ECG waveform after it's generated by Neurokit2. Or consider developing a custom model to generate these specific ECG morphologies and features. Make sure to adapt and test any code thoroughly to ensure it meets your specific needs and constraints and produces physiologically plausible ECG signals if that's required for your application.
Why do I need a more advanced?
For the PQRS and QRST delays in different ECG signal types, you might need to look for a more advanced ECG signal generation library or model, or adjust the ECG waveform after it's generated by Neurokit2. Or consider developing a custom model to generate these specific ECG morphologies and features. Make sure to adapt and test any code thoroughly to ensure it meets your specific needs and constraints and produces physiologically plausible ECG signals if that's required for your application.
So that cannot be modified, can it?
Yes, that's correct. Neurokit2 is a great tool for basic ECG simulation, but for more specific adjustments like PQRS and QRST delays or various ECG morphologies, you might require a more sophisticated tool or approach. Here are some options to consider.
Do we need to make custom model? We already had a custom model, but it was too simple.
Develop a custom model to simulate the ECG signal where you have complete control over every aspect of the waveform. You can use mathematical models, such as the differential equations-based models, to create a more complex ECG waveform, and adjust parameters like PQRS and QRST delays manually. There might be other Python libraries or tools that offer more control over these specific parameters. It's worth checking medical signal processing libraries and resources for more advanced tools. You can also manipulate the ECG signal generated by Neurokit2 manually to simulate the effects of different PQRS and QRST delays. This could involve shifting the parts of the waveform to simulate the delay or using signal processing techniques to modify the waveform.
No, I don't want to use pre-recorded real world ECG.
If the goal is to have a variety of ECG morphologies for testing or educational purposes, using a dataset of pre-recorded real-world ECG signals with various conditions might be an option. You can then apply noise and other modifications to these signals as needed.
Okay, so apparently it's not possible with Neurokit to change the morphology of the signal. Well, surely there is a way. I mean, it's a synthetic ECG. So ideally we would like to use a simple existing model. We don't want to create a new one. Suggesting using different libraries. What are the options? So manipulating the generated signal is a good idea. How do we do that?
There are a few Python libraries apart from Neurokit2 that you can explore for ECG simulation. ECG SIM is an application that allows the simulation of ECG as recorded in the body surface potential map, BSPM. It's a bit more advanced and detailed, though it might be too complex depending on your needs. OSEA, Open Source ECG Analysis, is another tool for ECG analysis that might potentially be useful for your needs. A more straightforward method would be to manipulate the generated ECG signal directly. For example, you can try splitting the generated ECG into different segments, P-wave, QRS complex, T-wave, and then apply shifts, delays to these segments. Here's a rough example of how you might manipulate the ECG waveform to simulate the effects of different PQRS and QRST delays. In this code snippet, the NP roll function is used to shift the QRS complex and T-wave to simulate the delays. Biophysical models can be complex as they simulate the electrical activity at the cellular and tissue levels to generate ECG signals. These models can represent various cardiac and electrophysiological conditions. However, implementing these models can be complex and computationally intensive. The cardiac myocyte, this model involves detailed cellular level physiology and is used to simulate the action potential of individual cardiac cells, incorporating a detailed representation of the ion channels and other cellular components that contribute to the electrical activity of the heart. For a simpler application or educational tool, directly manipulating the ECG waveform, or using a more straightforward library like Neurokit2 or OSEA, might be more appropriate. Displaying the generated ECG signal can be a practical approach, especially when you need to introduce specific changes or anomalies for educational or testing purposes. Below are some ways to manipulate the signal. Identify the P-wave and QRS complex in the ECG. Introduce a delay between the P-wave and QRS complex to simulate different P-QRS intervals. QRS-T delay. Identify the QRS complex and the T-wave. Introduce a delay between these two components to simulate different QRS-T intervals. You can also change the amplitude of specific waves, P-wave, QRS complex, T-wave, to simulate conditions like hyperkalemia, etc. Below is an enhanced version of the previous example, demonstrating the manipulation of an ECG signal with a focus on introducing PQRS and QRS-T delays. The above code is a simplified example. The actual implementation would depend on the complexity of the generated ECG signals and the specific changes required. More advanced signal processing techniques may be necessary for precise manipulation of the ECG waveform, especially for creating physiologically realistic modifications. Additional information about the ECG waveform structure and specific points, like the beginning of the P-wave, end of the QRS complex, etc., would help make more accurate adjustments. Make sure to validate any manipulations against clinical or physiological knowledge to ensure that the manipulated ECG signals remain realistic and meaningful for your application's purposes. You can disable those specific input fields and make them non-accessible by adding the disabled attribute to the less than input greater than or less than select greater than tags in your HTML. When an input field is disabled, it is unclickable, and its value won't be sent when submitting the form. Here's how you can update your HTML to disable the PQRS delay, QRS-T delay, and signal type options. I added the disabled attribute to the PQRS delay, QRS-T delay, and signal type input fields. This will gray them out and make them unclickable, indicating to users that these options are not available for the time being. Sure. This code snippet is utilizing the Neurokit2 library to simulate, process, and plot an ECG signal. Generating the ECG signal Python copycode ECG equals nk.ec_simulate, duration equals 15, sampling _rate equals 250, hard _rate equals 70. This line of code is calling the ECG_simulate function from Neurokit2 to generate a simulated ECG signal. Duration equals 15, the ECG signal will be simulated for a duration of 15 seconds. Sampling _rate equals 250, the ECG signal is sampled at a rate of 250 samples per second. It indicates how many data points are recorded every second. Hard _rate equals 70, the simulated heart rate is 70 beats per minute in this ECG signal. The generated ECG signal is stored in the ECG variable as a Numpy array. Processing the ECG signal. The ECG_process function is used to process the generated ECG signal. ECG, the raw ECG signal that needs to be processed. Sampling _rate equals 250, the sampling rate of the ECG signal. The function returns two outputs, signals, which contains the processed ECG signals and other derived signals, such as the R peaks, heart rate, etc., and info, which contains information about the identified ECG peaks and waves. Visualizing the ECG signal. ECG_plot is a convenient function in Neurokit2 for visualizing the ECG signal alongside its processed components like R peaks, etc. Signals, the processed ECG signals returned by the ECG_process function. Info, the information about the identified ECG peaks and waves. This function will generate a plot of the ECG signal and its identified components, which is helpful for visual analysis and verification. You can integrate a similar process into your Flask application by adapting this code into your generate_ECG route. Here's a modified version of your existing code to include ECG processing and to return the processed signals. The ECG signal is generated and processed using Neurokit2 as per your example code. The processed signal, signals, ECG_filtered, and R peaks, info, ECG_R_peaks, are included in the response JSON. You can choose what specific data to return based on your application's needs. Note, you should include appropriate error handling and validations as needed for your specific application requirements and constraints. Also, ensure that you have installed the Neurokit2 library using pip install Neurokit2 if you haven't already. You can integrate a similar process into your Flask application by adapting this code into your generate_ECG route. Here's a modified version of your existing code to include ECG processing and to return the processed signals. You can now return the processed signals or specific components of it. It seems you have combined two different approaches to generating and returning the ECG data. You first use Neurokit2 to process the ECG data, but then you also have another section where you manually add noise and other adjustments to the raw ECG data and return that. This may not be what you intended. Here's the breakdown and correction. Using Neurokit2 to generate and process ECG data. You correctly used Neurokit2 to simulate and process the ECG data, and prepared a response dictionary with the processed data. Manually adjusting the raw ECG data. After that, you also have a section where you manually add white noise and 50 Hz noise to the raw ECG data and then prepare another response dictionary with this manually adjusted data. You should decide on one approach to avoid confusion and redundancy. If you want to return the processed ECG data from Neurokit2, you should remove the second part where you are manually adding noise and adjusting the raw ECG data. Here's the corrected code. Ensure to decide on whether you want to use the processed ECG data or the raw ECG data with manual adjustments. Clean up the code to remove the redundant parts. If you still want to adjust the processed ECG data, like adding white noise, etc., ensure to apply those adjustments to signals, ECG_filtered, instead of the raw ECG data. Make sure to thoroughly test the application to confirm that it behaves as expected, and apply any necessary validations and error handling to make the application robust and useful.
So for that, let's have the working bit and move on. Comment this out. Yeah, we can comment that out as well. Test this, we'll publish this one. Do it now. How do we? Should remember how we did it. We did one yesterday. Published one application yesterday, so we should remember how to do it. So it's available on the site. It will be going into here. So let's see, we need that. It was the one we published yesterday, cross coherence. This file, we need a copy of that. Now, this is called ECG Gen. So case sensitive, of course. This is commented out, but we will change that anyway. Okay, so if we have this one, we should have info. Right, we need to edit this Apache configuration. Regenerate that. Have to edit. Edit.
Your WSGI file looks mostly fine, but there are a few details to consider. If you're facing any issues, you may check the following points. Make sure that all required packages, especially Flask and Neurokit2, are installed in the Python environment where the Apache server is running. Ensure that the Apache server has the necessary permissions to access the var www bionichaos ECG_gen directory and all its contents. Check the error logs of Apache to understand any issues during the start. The error logs can often be found in /var/log/apache2/error.log. Ensure your Apache configuration is correctly set up to handle the WSGI application. For example, you might have a configuration like this. Make sure the from app import app as application line is correct. Here, app should be the name of your Flask Python file, without the py extension, and app should be the name of the Flask instance in that file. Make sure the naming matches exactly. Don't forget to restart Apache after making any changes to the configuration or WSGI file. Make sure all application dependencies are installed in the environment where the application is running, especially if it's a virtual environment. If you are using a virtual environment, ensure to point to the correct Python executable within that environment. Add this at the beginning of your WSGI file. Replace path _to_your _virtual_env with the actual path to your virtual environment. Ensure that the required Apache mods are enabled. Ensure the file paths in the Apache configuration and WSGI file are correct and that the Apache user owns the files, or at least has read permissions. Check all the above steps and make adjustments as required. Make sure to thoroughly test in a development environment before deploying to production to avoid unnecessary downtime or issues.